Hi, I'm Ryan Nickel, CTO at DSA Ocean, and today I want to talk about setting up some multi-directional sea states in ProteusDS. So what do we mean by that? Well, when we look at Simulation Toolbox, a lot of the default sea state options here, the wave types, you have sinusoidal waves, airy waves, you've got a couple of different spectrums, John Swap, Pearson-Moskowitz, and custom spectrums, and so on. But sometimes when you're looking at real data from a deployment or an actual project, you'll see some really complicated combined spectrums where there's a swell that's going one direction and then a wind-driven, messy, choppy sea that's totally different frequencies going a completely different direction. So I'll show you a way that you can do something really complicated by adding up these different sea states together. Now, the key here is using wave states defined by wave feature. So if we go to wave type 11 and resolve follower properties, what you can do is create a wave feature. So we'll call this one first, well, we'll just call it wave feature 1 and go to feature definition. And what you'll notice when you do that is this wave feature has the same kind of inputs that you sort of saw in the environment input properties. So what we'll do with this one is we'll go John Swap. In this wave feature, we'll rename resolve follower properties. We'll say this one is like a significant wave height of 5 meters and leave it at 9 seconds. We'll leave this going at 0 degrees. That's heading to the north. That's pretty low wave segment, so maybe I'll increase that to 50. Then if we go back to the environment, you can add another wave feature. So you can just literally copy and paste this. We'll call this wave feature 2. And we'll go right click, go to feature definition. Now I haven't made wave feature 2 yet, so it prompts me to say, hey, we have to create this wave feature. And we'll do something similar. We'll do another John swap, but we'll make this totally different. So we'll resolve follower properties on this one, and we'll do this, this is going to be really wacky. We'll make it 90 degrees to this, and something really scary, 15 meter significant wave height, maybe 20-second peak period, and do 50 wave segments with that as well. So now I'm going to save this. Oh, yeah, we'll have to save it on just save it on the desktop here. Wave state. Select this folder, combined wave state. Okay, and let's run it. Now we have an empty simulation. There's no D-object, so it should run pretty quick. Now let's see what that looks like. Now, one thing I wanted to highlight when you do this is you lose a little bit of the meaning of the input states from what's actually being simulated. And what I mean by that is like, well, when you're specifying the significant wave height of the spectrum, the input spectrum, that's one thing, but now we're really like superimposing these two spectrums on top of each other. So the as simulated sea state is not going to be some obvious combination of, that 15 meter sea state and the, what was the other one that we did? 5 meter significant wave height. So you got to be a little bit careful about the meaning of doing that. But from an engineering perspective, this can be kind of helpful to kind of just get a sense of what's happening. We're going to make this, I'm going to go to edit water here and just make the water patch in engineering view look a little bit bigger to cover more area. And yeah, when we look at what this looks like, I mean, it's going to be really chaotic, sort of fake sea state where we have a whole bunch of energy going one way and going another way. So this isn't necessarily meant to be representative of a real sea state. I'm just highlighting that, you can combine these totally different spectrums together and get something that looks really interesting and might be sort of representative of something that you're looking at. It's a quick way of doing that. Now I want to also highlight by default, the environment always prints out, well, you've got this wave stats probe at 0, 0, the global origin. You can add as many more wave statistics probes wherever you want. So this is at the XY location of that probe. That's at the origin. If we go to the results folder, if you look at the wave stats probes.dat file here, you'll see a summary of the statistical information of the as simulated sea state. So this is something I wanted to highlight to you. This is the simulation time here, X and Y location of that particular probe. And then the as simulated significant wave height here is, almost 14 meters. Then there's a minimum height at that location. That's the sort of out of the time series. That's the minimum value. There's the maximum value. This is all in base, meters. Worst case peak to trough that came across at that point, so almost 15 meters. That's only in 60 seconds, so the longer it's going to be, the bigger these numbers are going to be. And then a mean up cross period as well. So this kind of helps you gauge a little bit about what's the meaning of that as simulated sea state. And there's ProteusDS is not doing anything fancy when it's combining these sea states. It's just superimposing all of the sinusoidal waves together. But it's an interesting way to make a combined sea state if you have some data that you're trying to kind of replicate really quickly and then do an assessment on a mooring system or something like that. All right, hope that was interesting and helpful. Thanks for watching.